All right, welcome back. Today we're going to continue our discussions on paper one, May June, further maths 9231. Right. Our first questions here. A curve C has an equation cos y equal to x. Now, given the domain x is greater than negative pi and less than pi. Right. So the task here is use the implicit differentiation to show that the second derivative of y with respect to x is given by negative cotangent y um, multiplied by the square of the first derivative. All right. And then secondly, hence we need to find the exact value for the second derivative d2y dx square at the point half and pi over 3 on the curve itself, right? Okay. Now, before we start with answering the question here, just a bit of touch up on the property of this curve. Now we are given cos y equal to x here, so cos y equal to x. Now, given that the domain is lying between here, okay, right. Now, first of all, how does this graph actually look like? Now, of course, implicitly it looks something like this. All right, now you may wanted to like restructure this so that you can get an explicit equation y in term of x. So it will look something like this here, right? Now, given that the domain is given here, all right, now you are wondering why the domain is given as such then, okay? And then what is the relationship to the cosine function itself, okay? So here I'm going to bring you back on how the graph of cosine look like in this case. All right, you can see that this is how the cosine graph actually look like, okay? Now, what we are looking at here is the inverse of cosine x. Now, for these cosine functions to have an inverse, it must be a one-to-one functions. But if you look properly, this is not really a one-to-one functions. Over this particular domain here. So it's not really a one-to-one function. Now, therefore, usually we would like to set this function so that it would be one-to-one. So in order for us to set these functions to be one-to-one, now the domain for the original cosine. Right? So I'm talking about the domain for the original cosine here. Okay, just let me write it down. So the original cosine, the domain for cosine would be, in order for us to get an inverse functions, the domain must be lying between. Okay, now let's take a look at using theta here. So the theta should be, now based on my preference here, I will set it starting from 0 um, until a pi, then pi over 2. Okay, let me see whether I got it correct. Okay, sorry, over pi, my bad. Hold up. So I should actually restrict the domain theta greater than 0 and then go up to a pi there. So that is actually this piece of graph starting from here until here. Now you can see that it's actually a one-to-one. Right. Now our intention here, okay, now my equation is cosine theta. So now I intend to obtain the y equal to the inverse functions of cosine. So the inverse function of cosine, basically a reflections of the cosine about the line y equal to x there. So that's just a recap. Now let me show you how does it look like here. So first of all, you must have the reflection line. So this is y equal to x, okay, and then we're going to reflect this piece of graph about this line of reflections. Now, of course, before that, we have already restricted the domain between 0 and pi here. So restricting the domain would actually give us this piece here. Oops, sorry. would give us this one here. Okay, so this is after restricting the domain between 0 and pi here. So now you can see that this is a one-to-one function. We're going to reflect this function one-to-one about y equal to x, and then this is a result after reflection. Okay, you can see that. All right. Now this is the graph that we intend to get for y equal to the inverse functions of cosine. So this is the graph that represent y equal to inverse cosine here. Right. So I hope that is clear. Just to recap on how the inverse function actually look like, how this function actually look like explicitly. So it look explicitly in this form. Right. Okay. So now we are ready to actually obtain the first derivative before we obtain the second derivative. Now the first derivative for this, you could actually differentiate this explicit function here, but it would be quite challenging to actually differentiate this explicitly. So it's always nicer or more comfortable to differentiate this implicitly. So we're going to start off from here, cos y equal to x. Okay, we're going to differentiate this implicitly, both sides, with respect to x, of course. Okay, so uh, that's how the implicit differentiations look like. All right. Now, if you want to recap how this implicit differentiation look like, we can actually do it this way. So we can I'm going to go through the formal way how these implicit differentiations would actually look like shortly, but I'm going to show you the result first. Okay, so differentiating this with respect to x would yield a negative sine y dy dx, and then that would yield a 1 here because there's only an expression of x here. Right? So from here itself, our dy dx will be negative 1 over sine y there. Alright, so I hope that is clear. That is how we obtain our first derivative with respect to x as a negative 1 over sine y in this case. Okay. Alright, now that's the first derivative. We're going to move on with the second derivative. Okay, let me um, clear this up. Okay, and then we're going to move down here. And then now the second derivative. Okay, now the second derivative we could start by differentiating it from here, for instance, or you could actually start to differentiate from here. Doesn't matter where you start off. For me, I prefer to start from equations number 1. So I'm going to write down here from 1 itself. Okay, so I'm going to differentiate this implicitly one more time with respect to x. So that will be sine y dy dx. Okay, so there you have it. Now from here, this will be a bit challenging because it involves products rule. Okay, so we're going to do this one at a time. So let us maintain this one first and then differentiate this. So if you differentiate that, that will be the second derivative. And then secondly, we are going to differentiate this now, maintaining the dy dx. So differentiate this would give us cos y, and then dy dx. Okay, so if you differentiate this, you get negative cos y dy dx. And then we also have another piece of dy dx over here. And then on the right hand side is a piece of cheesecake. It's just a 0 here. All right, this is what we have. And then of course I'll do a bit of rearrangement. So this is d2y dx squared, negative sine y, negative cosine y. This will be dy dx square. Right? I hope that you can see this. And then after that, of course, we can rearrange it further. It will be d2y dx square sine y here will be the same as negative cosine y dy dx square. And then therefore, we're going to conclude that Therefore, the second derivative is given by, all right, now negative cosine y over sine y is actually negative cot10. And then there you have it. All right, now maybe it's better if I write down the intermediate step so you can see that. Right. In terms of exam, it's always best to show all your working. So here we have dy dx square, which is the same as negative cot10 y dy dx square there. All right. Now that's the proof that we have managed to or successfully shown here. The second derivative is given by negative cotangent y multiplied by the first derivative to the power of 2. Right. So I hope that is clear. Okay. Now, next I'm going to show you a bit of how we actually apply the implicit differentiation. So for that part, it's just to recap. So I'm going to show you how do I actually obtain this result here, result number 1, right? So before that, let me erase off this. Okay, so just to recap here, we're going to consider equation 1. So we can consider equation 1 here. Now, by differentiating that implicitly, okay, so by differentiating this implicitly, what we are saying is we are going to let u equal to cosine y, for instance, okay, and then we can actually differentiate this with respect to y first. Of course, it's quite easy in this case, which is negative sine y. There is no introduction of dy dx at this point because we are differentiating with respect to y here, right? So we have to pay some respects to the y. Maybe that is why. Okay. Right. Now next, we are going to consider the left-hand side of this equation 1 here. So the left-hand side for this indicate that we are differentiating this, which is the same as du dx. All right. Now by using chain rule, this is the same as du dy by dy dx then, since u is differentiated before this. So you can see that we have du dy given as negative sine y in this case, and then a y in term of x. So therefore, from here you will be able to obtain sine y dy dx. Okay, now that's a bit of recap to show you how do I reach this section here by using chain rule, right? So I hope that's clear. We're going to move on to the second section shortly. All right, now that we have successfully proved that the second derivative is given as such, hence we need to find the exact value of the second derivative at this specific point on the curve itself, right? Now I'm going to rewrite this second derivative one more time. So we have okay, our second derivative. Okay, second derivative, and then from here at the point half pi over 3 on the curve C. Okay, on the curve C, the value of x is half. The value of y is equal to pi over 3. So you might want to write explicitly so that you can do some substitutions later on. Okay, so from here, all we need to do is just substitute this value into my second derivative. So therefore, my second derivative would be negative cot10 pi over 3. And then my first derivative. Okay, now we have actually obtained our first derivative previously. Our first derivative was 1 over sine y. So I hope that is clear. So from here, we can determine the first derivative first at x equal to half and y equal to this. So therefore, that would be negative 1 over sine pi over 3. Now pi over 3 is 60 degree. So that would be a sec 3 over 2. So we'll write it down here shortly. So there's sec 3 over 2 like this. And then of course you can simplify that as a negative 2 sec 3 over 3 if you want to rationalize that, right? So therefore this is our first derivative. I'm going to write it down here. Okay, so we obtain this first derivative from here. Now we're going to square that. And then cotangent 60 degree is the same as 1 over tangent 60 degree. All right, so therefore this is what we have, square. And then tangent 60 degree is basically sec 3. Okay, now here we will have a 4 by a 3 by a 9 here. All right, so that's how it actually look like here. And then finally you can simplify this as negative 4 over 9 sec 3. Okay, now that will be our answer for our second question. Right, now I hope that is clear. It's a very straightforward question, given that we knew the first derivative and the second derivative. Now don't forget that you have to work out the first derivative, and that we have already obtained the second derivative from the first derivative. So that's how we managed to reach this conclusion here, right? So I hope that's clear. I'm going to move on to the second question shortly. All right, just before we move on to question 2, this is just a little properties of or the purpose of why we are attempting question 1 here, right? So here I'm going to sort of give you a geometrical view of the first derivative dy dx and its second derivative d2y dx squared here, right? Okay, now in short, the dy dx, the purpose of evaluating dy dx is for us to be able to evaluate gradient. So the main purpose is to evaluate gradient of tangent gradient of tangents to the curve at a specific uh, point or points. So at a specific points. Sorry. Okay, so that's the main purpose of using dy dx here. Of course, if you are dealing with straight line equations or straight line functions, then there's no point performing dy dx because the gradient of the straight line can be obtained from the structure of the equation itself, right? So it is more useful when you are dealing with a curve, a more complex form of a curve, right? Now, secondly, the second derivative, d2y dx squared, is used to investigate the concavity of the curve. So to study the concavity of a curve, usually is over certain interval, over certain intervals there, right? So I'm going to illustrate to you visually what do I mean by gradient or tangent here, right? Okay, now you can see that okay, we can start from any position x as you like, for instance. So take for instance, if you start from position x equals to 0 here. Now we can actually draw a tangent line. So this blue line represents the tangent. So therefore, this tangent has a gradient of -1. You can see that it's sloping down. So it has a gradient of -1. And then that is the way how we evaluate gradient, which is the ratio of rise over run in this case, right? And then by evaluating its d2y dx squared, we found that it's equal to 0 here. Now this actually shows us the concavity of this curve at this position here, right? Now if you get a unique result as a second derivative equal to 0, there is a special name for this position here, or this point. This is called the inflection, or sometimes they call that saddle point, right? A way where its second derivative is equal to 0 here, right? So as we change the position, for instance, as we change the position for the x itself, so take for instance, if I move up here, you can see that the gradient still remain as negative, but there is a change in its concavity. Now you will notice that starting from x equal to 0 to the left, so anything less than 0, the concavity is always positive here. And then do recognize the shape. So generally you will see that the shape to the left of 0 here would always look something like this. Right. This is what we call as the concave. All right. Sorry, not concave, convex. Right. So if you have a geometrical structure that looks something like this, we call that this is a convex property. So the concavity, which is its second derivative, will help us to recognize the structure of the curve itself. So we know that for that interval ranging from anything less than 0, for instance, anything less than 0, the curve is a convex curve. Right, so that's the purpose of using its concavity here. And then if we were to change the position x over the positive value of x, you will notice that the gradient is still negative, but the concavity become negative in this case. Right. So what does that actually mean? If you look at from starting from here, the shape looks something like this. This shape here, there is a name for that. So since we call this as a convex, then we will call this as concave because it looks like a cave shape, right? So when will we get a concave structure? We will get a concave structure when the second derivative is actually less than 0. Okay, but for this case, the gradient is still negative. All right. So I hope that give you a geometrical perspective of the evaluation of first and second derivative of any curve, right? Okay, that conclude our first question, right? We're going to move on to a second question shortly. All right, let's take a look at question 2. This is another level further maths problems related to summation of series. All right, let's take a look at this. Now, before we start with solving this problem here, there are a few identities that we need to develop here, right? So the identities that I'm going to develop for you to see and for you to use to solve this problem here, right? So in this case, this form basically looks something like this form here. Okay, now the format looks something like this. This is like sine A sine B form divided by, for instance, cos C plus cos D format. So here I'm going to develop a formula for us to use for this and for this. Right. Anyway, both of these formulas are indirectly found in this data booklet here, in the data booklet MF19. Right. But I'm going to show it to you how we can deduce it manually and then use it in exam. All right. Now, if you deduce it and use it in the exam, well, the marks will be more than 2 then. Right. So let's take a look at how to work with this shortly. So I'm going to erase this. I'm going to show you how to derive both of these um, trigonometric identity so that we can use it directly. Right? Stay tuned. Right, now the first part, we're going to consider the numerator. So the numerator is given by such. So here I'm going to let A be n minus 2, sorry, n minus half, and then B equal to a 1 here. So it's easier to refer to. Okay, now I'm going to use one of the trigonometry compound identity for cosine. So I'm going to use cosine A minus B, for instance, is equal to cos A cos B plus sine A sine B. Okay, this one you can get it from the data booklet. And then that will be our first equation here. Now, the second one is the same identity, but instead of using minus, we're going to use a plus here. Okay, so that will be cos A cos B, subtract instead. Right, now that will be our second equation. So here we're going to solve this simultaneously so that we can get a form of the products between these both sign. So you can see that from here. We can take 1 subtract 2. So if we take 1 subtract 2, we will have this as a 2 sine A sine B. Okay, so if you subtract this, it will be 2 sine A, 2 sine B. All right. Now, there's a 2 already. So since there's a 2, I might as well consider this then. It will be much more direct in this case. So therefore, the 2 sine A sine B is actually equivalent to cos A minus B, subtract off with cos A plus B. Okay, so there you go. This is our identity that we can use now. Since A is equal to this, now I'm going to substitute this value inside here. Therefore, we can deduce that sine n minus half sine sine 1 in this case must be the same as cos A plus B. So your A plus B is this n minus half minus 1. Is that correct? Minus 1. Did I get it correct? Just let me check. Cos A plus cos B. So the A is this. The B is... Oh, all right. I think this one's supposed to be a half. Sorry. Let me correct that. I think based on the question itself is half. All right. Now I accidentally write this wrongly, so that's actually a half. So we are considering 2 multiplied with sine n minus half sine half here, where the b is a half. So therefore I'm going to minus by half here. So that's our b. Subtract off with cos a plus the half here. All right. So from here you can see that this can be reduced to n minus 1 now. Subtract off with cos n. So therefore, this expression here can be simplified into this form here, right? So I hope that is clear. Now the second part. We are going to consider consider this one here. So for the second part, we're going to consider what am I supposed to consider here? So we're going to consider the cos 2n minus 1 plus cos 1 here. So this is the denominator. All right. Now using the same identity here, all right, using the same identity, we notice that this is actually cos A plus cos B, actually. Cos A plus cos B. All right. So now we're going to consider this, and then I'm going to work it out separately then, right? Because it's quite long here. All right, so maybe I'll just stop at this point. I'm going to erase all this. All right, now I hope the first part you are clear. This is the result that we obtained. All right, now I'm going to analyze and consider the denominator, and then uses the same identity here to simplify the expression. All right, stay tuned. All right, now next we're going to consider the denominator. right, which is given by this expression here. Well, let C equal to 2n minus 1, D is equal to 1 here. By applying the same compound identity instead of using A and B, so that we don't um, conflict with the previous numbers there. Right. So from here, we are going to solve this simultaneous equation. We are going to have, since we are using a additional rule here, we will use 1 plus 2 here. Okay, that would yield cos s plus c plus d. And then if you sum up these two equations here, we will end up with 2 cos c cos d here. All right. Okay, but anyway, if you compare this form and this form here, all right, now we notice that there's only one term here, so we let our c equal to this, d equal to this, right? Okay, so now you may find it a bit different here. So what we can do is instead of using this directly, we can rewrite that. So 2n minus 1 plus cos 1 can be written as, so in this case we can write as, if you want to write in this format here, for instance, you can see that your c is actually indirectly is like 2n, and then your d is actually a 1 here, right? If you actually do that, right, then this one would not really tally then. Okay, so one way to go about this is, okay, yeah, I think we do it this way, it'll be much more easier here. So now, of course, in the exam, we are not going to derive this. In order to do this, we will let, in this case, we'll let P, okay, because this is just C alone. Let me see. Okay, let's C and D. Okay, that's cool. So instead, we are going to let P equal to C minus D, for instance, whereby the Q would be equal to C plus D then. All right. So from here, I'm going to create another simultaneous equation here, number 3. This is number 4 here. And then by solving this, you will find out that the C itself, okay, so the C itself is basically half a P plus Q, and then whereby the D itself is half P minus Q, then, P minus Q then. Right. Okay. All right. Now, okay. So this is what we have at this point of time. So, instead of writing that as C minus D instead, so we can actually convert equations number 2.5, for instance. So we can actually convert these equations 2.5 into this. So we can convert this into this. Now you can see that that become cos, is it cos P? Yeah, correct. Cos P plus cos Q is equal to 2 cos. The C instead now will become half P plus Q. The D would instead become half P minus Q. Right. So comparing this one with this one, it'll be much more easier to work with. Right now, using this analogy here, you can see that cos 2n minus 1 here, which is the same as this now, plus cos 1, okay, that would be the same as 2 cos half. So it's actually P plus Q. So this is P plus Q here. So if you add them up, it's actually 2n. And then cos P minus Q. So P minus Q is actually half 2n minus 2 here. And then if you deduce this and simplify that, it will become cos n. cos n minus 1. All right, so there you have it. We managed to simplify this into a more manageable form. All right, we are going to refer to our first result just now, the sine. So I'm going to write down here sine n minus half, sine half here is equal to the result that we have deduced just now is n minus 1 minus cosine n here. So this is the numerator, this is the denominator. Now we're going to simplify the whole expression shortly. All right, here we go. Let's refer back to the questions one more time. And now these are the results that we have derived from our previous trigonometry compound angle identity. So this is the one that we have for our numerator. And then this is our denominator's result. Of course, this is 2 times of this. All right. Now, therefore, from here, I can write down un now is actually 2 times 2 sine n minus half sine half here. All right, so you can see that. And then the whole thing divided by the denominator plus cos 1. All right. And then this whole thing can be simplified using the right hand expression here. So we can write it down as divided by, okay, so we have here cos n. All right, there you have it. And then right after that, we can simplify the 2, of course, and then divide and conquer this expression to produce its partial fraction. So therefore, this will become something like this now. Okay, so you can see that from here, we can reduce this. Therefore, okay, therefore we can simplify into this form, which is as required. Okay, now of course, in this case, I do need to make remark that cos n is not equal to 0, and then at the same time, when I reduce this, n minus 1 should not be equal to 0 there. Right. And then there you have it. We have managed to prove the first identity. All right. We're going to use the identity proven here to obtain the summations of this series. Right. So once we have proven the identity for the sequence here, we are going to make use of this result using methods of differences to find the summations of this series. All right. So therefore, I'm going to write that down here. Un. So the sum of this series is given by. We're going to sum it up until n term here. So that is basically the same as this, because un is given by this. So I'm going to write that down as this. Okay, and then maybe it's best if we put a bracket across here. Then you're clearer. All right. Okay. Now, what this actually mean? We still need to elaborate, sort of give more detail to these summations because this is a simplified form here. Now, if we try to give more detail here, okay, maybe I'll try to write down at the side here. It'll be easier. That basically means 1 over cosine 1 minus cos 0 here. Okay, now that will be our first term. And then we're going to sum up with 1 over when n is equal to 2. Okay, so when n is equal to 2, that will be 2 minus cosine 1. Right now, that will be the second term. And then after that, we're going to continue on with the third term. So you can see that this one will be 3 minus cosine 2. And then, of course, we're going to continue on with these summations. And then, okay, I think I put it down here easier. So we're going to continue its summation here until we get something like this. So I'm going to show a last term from the back. We will start off from n minus 1, then it'll be easier, I think. So n minus 1 will be easier to gauge here. So we will let n equal to n minus 1. So therefore, we have the second last term here. That will be cos n minus 2, of course. All right, so we're going to sum them up. Okay, and then after that, we have the n term up to n. Okay, now this is my mistake. One more time, I forgot to change the label for the number of summations that I'm trying to sum up here. This one's supposed to be n minus 1. This one will be n minus 2. And then when we reach the last term, this is the expressions that I'm getting. That will be n minus 1 then. All right, and then there you go. And then you notice that from here, we sort of can eliminate this term and this term here. Okay, you will notice that this one can also be reduced with the previous term, and then at the same time, we can reduce this. And at the same time, we can also reduce this with the previous term here. Now, by doing so, um, yeah, don't forget, we can also reduce oops, I think I reduced the wrong, oh yeah, correct. So we can also reduce the cos 2 with this one here. So all along we have actually eliminated every single intermediate expressions that we have here, except those that I did not eliminate, like this one and this one. So therefore I can simplify this whole entire summations to I only left with this and this. So therefore I can write this down as cos n minus of cos 0. Cos 0 is actually a 1. So therefore, doesn't matter whether this is degree mod or radian. So that is basically a 1. And then therefore, we managed to deduce an expressions to represent the summations of this series here. Right? So I hope that is clear. I'm going to move on to the last section shortly. Right, let's look at the last sections for this question here. We need to explain why the infinite series u1 plus u2 plus u3 until infinity does not converge there, right? So now u1 plus u2 plus u3 and so on and so forth can be written in the summation form as un, okay, hold on. Okay, can be written in a summation form as using limits here. So as n approach infinity here. So I can use the summation here. So n is equal to 1 until n un here. So that is basically representing the summation of all these sequences. And then we know that we have obtained the expression for this summation series. So therefore, we have this approach infinity, and then the summations of this series is given by cos n here minus 1. All right. Now we know that cos n is a periodic. Okay, it's a periodic function. So cos n is a periodic functions, therefore it always fluctuates between 1 and -1, right? So maybe it's best if I show you that. Okay, just let me get my GeoGebra here. Okay, let's move it over here. It will be easier to see. Okay, so let me try to plot the graph 1 over cos x here. Now you can see that this graph is actually a periodic graph, periodic function in this case. So it's always fluctuating between anything more than 1 and then anything less than -1. Now, because the value is always fluctuating here, so therefore the summation series will not converge to a specific value here, right? So that is the main reason. I'm going to write down here. Since cos n is a periodic functions, therefore um, there will not be any limits here. Okay, so therefore this is a periodic function also. And then because it's a periodic function, it fluctuates up and down. Therefore, we can say that u1 plus u2 plus u3. So here the limit n approach infinity, 1 over cosine n minus 1 does not exist. So we are saying that the limit for this does not exist. Therefore, does here maybe I'll write down here. Therefore, u1 plus u2 plus u3. So this summation series does not converge. Alright, so I hope that's clear to you. Until I see you again, thank you very much for watching. Alright, let's look at question 3 here. Right. So we have the lines L1 and L2 have equations given in its vector form. Right, now both of these respectively, this is line 1, L1, this is line L2 respectively. Now the point P on L1 and then the point Q on L2 are such that PQ is perpendicular to both L1 and L2. So you can see that from this diagram here, the red one is L1 and then the blue one is L2. P is on line L1, Q is on line L2 there, and then both of them are perpendicular to to both the lines respectively. Okay, here I can show you that. Okay, this is how it look like. Okay, so they are perpendicular in three-dimensional perspective here. So you can see that both the line PQ is perpendicular to both of these line L1 and L2. Okay, hold on. Let me change that. Okay, maybe this view or that view doesn't matter in this case. So maybe I change the view a bit. So let me change the view here. So you can see that this is the three-dimensional view. Here I can label this as L1 here. This is L2. So both of this line PQ is perpendicular to the line L1 and L2. All right. So the first thing we need to identify would be the directions for this line L1. So the directions for this line L1 is given by it's given by its directional vector, which is 1, 1, 0. and then the directions of line L2 is given by this directional vector, um, 0, -6, okay, and then 1 here. All right, okay. Now let me rewrite the equations again. So line 1 is given by R, and then line 2 is here. All right. So first of all, point P is on line L1, so we can actually obtain the um, position vector for P as this. Okay, this is position vector P, whereby the position vector Q is found on line L2, will be given by this equation here. So 4, and then a mu here. Right. Okay. Now we need to form the relative vectors or position vectors for PQ in this case. Relative vectors for PQ that is given by OQ and OP. Okay. Now that would be -2. Is that -2? Yeah, -2, negative lambda. We have here a 2 minus a lambda minus a 6 mu. And then finally you have mu minus 7 here. Right, now that will be the relative vector for PQ. Okay, now we know that PQ is 90 degree or perpendicular to line P1. So therefore, we know that the position vector or the um, relative vectors PQ is perpendicular to line L1. So therefore, it would satisfy this probability. Sorry, not probability. It would satisfy this property that the product of these two vector, the product of the vector PQ with its directional vector for line 1 will be equal to 0 here. Okay. All right. Now from here, we're going to substitute all the result that we have. We have this. And then I'll perform a scalar product with its directional vector, which is 110. Should be equal to 0 here. Okay, now that will yield -2 negative lambda and 2 minus lambda minus 6 mu here equal to 0. All right, so from here we have let me see what we have here. This one is cancelled off, so therefore you have lambda equal to negative 3 mu. Okay, now that will be our first equations that we can obtain, knowing that line PQ is perpendicular to line L1. All right, so I hope that's clear. Now next we are going to obtain another set of equations because we know that PQ is perpendicular to line L2. Okay, now I'm going to obtain that. Okay, so before I do that, I'm going to write this result up here. So from here I should be able to obtain lambda equal to negative 3 mu. That's our first equations there. All right. Now for the second property, we know that PQ is also perpendicular to line L2. Therefore, the scalar product with the directional vector 2 must be equal to 0. Okay, now that would be -2 negative lambda with its directional vector 0, 6, and 1. would be a 0 here. So therefore we have 12, 6 lambda, 36 mu, and then plus a mu minus 7 equals 0. Right. Now let's see what do we have here. We have 6 mu plus 37. Here we have 19. Right, now that will be our second equation. Alright, so I hope that is clear. Now from here onward, all we need to do is just to solve these two simultaneous equations here. Right, now I'm going to show you how to solve it. Now before that, I'm going to erase all this. So I'm going to write down my second equation here. So we know that PQ is perpendicular to line L2. That will yield 6 lambda equal to 19. That will be our second equations. Okay, so maybe I'm going to write this one down for reference. Yeah, I'm going to write down the equation first. So here you have 6 lambda is equal to 19. And then the relationship between the scalar product is here. Okay. Right, now all we need to do is just solve this simultaneous equation. So that shouldn't be challenging at all. So from here we have negative 18 mu plus 37 mu equal to 19 here. All right, so therefore that would be 1 for sure. Okay, now since mu is a 1, therefore the lambda will be a negative 3. Okay, so from here we can conclude that the position vector of P is given by this equation here. So there will be a 7, 3, and 7, whereby the position vector for Q is actually given by, oops, I think I substituted the wrong value here. So hold on, just let me correct that. That should be a lambda negative 3. So that should be a 3, negative 1, and 7. Okay, and then for all Q, there will be a 4, and then negative 2, because that's a 1 here, and then there's a 1. All right, so there you have it. How do we apply the scalar product to obtain the position vector for P and Q, where the line, the vector PQ is perpendicular to both the line L1 and L2. All right, so I hope that is clear. We're going to move on to the next question shortly. All right, let's take a look at question 4. All right, now this is a reductions formula. Okay, now it is given that for any n that is greater than or equal to 0, the reduction formula is given as such. So we need to show that the I2 is equal to 1/3 of e minus 1. Okay, now let's look at number 1 first. All right, so 1. Okay, I2 basically means this. So x2 ex3 here, dx 0, 1. Okay, so that's what it meant. And then from here, you can use the substitutions methods. Okay, so by using substitutions method, here we can say that let u be x cubed then, for instance. Okay, now the differentiations of u with respect to x is given as such. Okay, and then from here we can see that if you rearrange this, okay, if you rearrange this, that would actually give us 1/3 of du is actually equal to x squared dx. Okay, so that's how it looked like. And then furthermore, when x is equal to 0, okay, so we have to find out. So when x is for x equal to 0, now we are trying to change the lower boundary and the upper boundary. So for x equal to 0, we know that our u is equal to 0 here. Now when x is equal to 1, now your u is equal to 1. Okay, so now we're going to transform all this expression of x in term of u. Right. So from here we're going to change that. First of all, the boundaries we will have to change that. So the boundary now is in term of u. So from 0 to 1. That's still the same in this case. Right. Now the x square dx. You will notice that x square dx. X square multiplied with dx is actually 1/3 of du. So therefore, this expression here, x cubed is a u, so you can change it to u. This x squared multiplied dx is actually 1/3. So there's 1/3 of du. And then of course, rearranging that, you will get this. Okay, so there you have it. And then you can integrate this as if you are integrating the function with respect to x. Now, therefore, the answer for this will be EU from 0 to 1. Okay. From here, all you need to do is just substitute the upper boundary, which is E1, minus E0, which is a 1. Therefore, it has been proven. So we have managed to show that I2 is actually equal to 1/3 E minus 1 there. All right, so I hope that's clear. Now, next, we're going to move on to the second section. Okay, second section. Yeah. Now show that for n that is greater than or equal to 3, where in this case n actually refer to integer number, we need to prove that this expression is correct. So 3in is equal to e minus n minus 2 multiplied by the reduction formula of I n minus 3. Okay, so how are we going to do that? All right, now we're going to start from here. So first of all, we're going to start from I2. So this is IN. IN can be written as x n minus 2 here. Multiply. Okay, let me write down the original one first before I try to transform that. Okay, this is the original expression. You can restructure this so that it looks something like this. Okay. Now, of course, there are many ways to actually integrate this, right? The main reason why I write it down in such a case is because previously I have proven the first sections using this I2. So I noticed that there is a pattern that I can work with here, which is x squared e x to the power 3 there. Right? And then by introducing x n minus 1, that is typically an xn. Okay, but by introducing this x square, I will be able to integrate this. Right. Okay, now how are we going to do this? Now, usually student would start by using the integration by parts. Okay, now there are many approach to integration by part. Some students might like to use a formal way to do it. So I'm going to show you the formal way to do it so that you can follow step by step. In this case, you will let the u that you want to differentiate. So in this case, the u is x minus 2, okay, whereby your dv dx is actually equal to this one here. Oops, I accidentally write extra term here. Okay, so the dv dx is equal to this. Now from here onwards, when you differentiate u with respect to x here, we will get n minus 2 x n minus 3. Okay, so n minus 3 there, all right? And then next, the integrations of du dx so that we can obtain the v itself. Now that will be this. Okay, all right, now that will be that. Okay, And then we have done this in the first part there, right? So we have done this. This is actually equal to this value here, right? If we put the lower boundary and upper boundary, right? Now, therefore, the formal notations for this would be if you apply the integration by parts using these sections here, it would be x n minus 2 and then multiply by the integrated versions for this, which we already found out just now. It's actually third one third of EU actually from the previous one. I just show it to you one more time here in case you have forgotten here. So I2 is actually the integrations of EU du from 0 to 1 here. Yeah, so that is our integrations there, right? And then from here, we know that the okay, so from here you can actually put in how do you want to do this? Let me see. That would typically be x cubed, okay, because this is we use the u equal to x cubed previously. So therefore, you can actually substitute this x cubed back. Now that would be this 0 to 1. Okay, 0 to 1 here. Now that is our first um, part of the integration by part. And then, of course, minus of one third of the n minus 2 x n minus 3. And then the same thing, I will get e x to the power of 3 dx, yeah, from 0 to 1. Okay, so I hope that is clear at this point here. Okay, now if you are unsure how do I actually reach this, this is how we get there. Okay, I'm going to show it to you from here. Instead of using the u itself, okay, we can actually write it down in such a way. So the v itself is actually equal to one third of 3x squared ex3 dx. That's the one that we have. And then when we integrate that, that will become, if you use u as your substitutions, for instance, or you can actually do it this way. Usually I like to do it this way. Oh, oops, I think I wrote it down wrongly. Hold on. Usually I prefer to do it this way. Okay, because the dx cube here, dx cube basically means you are trying to differentiate the x cube. If you differentiate the x cube, you are actually getting 3x squared. So this is actually 3x squared. The reason why I write down in this case is because if you let this equal to u, for instance, then this will be u. Therefore, integrating this is basically one third of ex cube, actually. So that's how I managed to get this ex cube over here. Okay. Oh yeah. By the way, if you have forgotten about the formula for integration by parts, the formula for integration by part is given by this. So any integration by parts, we can integrate using uv minus minus v du dx multiplied by dx. Okay, now there's the original formula for integration by parts. Okay, now if you are unsure, you can always refer to the data booklet MF19 there, right? Okay, so from here itself, all you need to do is just substitute the upper boundary and the lower boundary. So knowing that x equal to 0, we'll use 0. And then if I put a x equal to 1 there, I would typically get 1/3 e then. And then I will be continuing this section here. And then I know that this is n minus 2. Yep, definitely. And then you will notice that since this is in x to the power n, and then this is x to the power n minus 3. So therefore, we can write this term here in the reductions formula format, which is I minus 3 because the pattern is exactly the same as this. It's just that the index is n minus 3. Yeah. Okay, so there you have it. I'm going to rewrite my IN here. And then, of course, if you like to rearrange that properly, so that will be IN equal to E minus n minus 2, IN minus 3 there. And then there you have it. We managed to prove this reductions formula. Right. So I hope that is clear. You might want to review again on how to perform integration by parts here. Okay, so I hope that's clear. I'm going to show you the last sections which utilize this result here. All right. All right, last sections of question 4. Okay, third sections here. Now we need to evaluate the exact value of I8. So I8 by using this result that we have proven just now. So 3I8. So if you put n equal to 8, so that will yield 3I8 is equal to E. The n is equal to 8, so that will be a 6. And then the n is equal to 8, so that will be equal to 5 there. Now this is what we have, our first equation. Now nothing much we can do about this. Next we're going to deal with I5 since we need to get a 5 itself. So we will let n equal to 5 now. Therefore we will get 3 and 5. Alright, 3 and 5 is equal to E. 5 minus 2, which is a 3. And then 5 minus 3, which is a 2 here. Okay, and then we knew that the I2 is given here, so therefore we can substitute this. Therefore that is 3 by 1/3 E minus 1. And then you will notice that this is typically just you can cancel off, and then therefore that is actually a 1. And then that would actually yield I5 equal to 1/3. Okay, since I5 is 1/3, therefore from 1, we found that 3I8 is equal to E minus 6 by 1/3, which is E minus 2. Okay, which is E minus 2. And then from here, we can conclude that I8 is given by 1/3 E minus 2. All right, now that concludes the exact value of I8. All right, now stay tuned. We're going to move on to the question 5 shortly. All right, question 5 here. You can check this question out. Okay. Here we are given a curve C is defined parametrically by these two parameters or parametric expression in term of t. So the x can be described in term of t, and then the y can also be described in term of t, where the t satisfy this domain here, ranging between 0 and 1. Now the area of the surface generated when the curve is rotated about through 2 pi radians about x-axis is denoted by s. Now therefore we need to show that the surface generated when the curve is rotated through 2 pi radian about the x-axis is given as such. So we're going to prove the first one. All right. Now before we move into proving this, now there are a few things we need to remember. First of all is the formula for surface area. So formula for surface area is 2 pi y square. In this case is 2 pi y, sorry, 2 pi y, and then multiply by the length of arc. So in this case, let me make it a little bit different. This is a lowercase s. So lowercase s is the change in the length of arc, or arc length in this case, right? All right. Now and then because the domain of t is set between 0 and 1, so therefore we will put as 0 and 1 here. Okay. Now that's in terms of t. You won't be able to see any t at this point here, but okay, bear in mind the ds is actually given by this parametric equation. So that is dx dt square plus dy dt square root dt. Okay, so you can see that ds is actually given by this, right? So we're going to substitute this one here. Now, of course, that will be something like this. So y, okay, so y, and then dx dt square plus dy dt square dt integrated from 0 to 1. Okay, so that is how the formula for, sorry about this, okay, formula for the surface area that was generated by rotating the curve 2 pi about the x-axis. Right. So now all you need to do is work out the um, differentiations of x with respect to t and differentiations of y with respect to t here. So we're going to do that. Now from here, dx dt. Let's do dx dt here. Okay, dx dt, there are many ways to do this. The quickest way is by using a chain rule. Chain rule will be the easiest method here. So you can see that by using chain rule, you should be able to get -2 over et minus e negative t here, and then to the power of 2. Right. So I hope that is clear at this point. Okay, now that will be our dx dt, and then of course the dy dt will be a bit challenging, but shouldn't be that tough in this case. Okay, so one way to do it, yes, you can apply your quotient rule, for instance. So by using quotient rule, I should be able to obtain this. Okay, let me try out. And in this case, you have et plus e negative t, and then that will be a square minus of et minus e negative t multiply also a square, and then that would be et plus e negative t squared. Right. So the numerator can be simplified. Of course, in this case, you will get. Let me see here. So you will get a 2et, and by the other one will be also a 2e negative t here. Okay, so there you have it, and then these two can be cancelled off. Therefore, that is actually a 4et plus e negative t square. All right, there you have it. That will be our dy dt. And then we're going to substitute this one into here. Yep. Okay, so by putting this into here, our y is this. So we're going to substitute everything that we have. For y, it'll be et minus e negative t over et plus e negative t. Okay, now that is from 0 to 1. And then the square of this, that will be a 4 et minus e negative t to the power of 4 plus 16 here, because it's square, et plus e negative t also to the power of 4, and then that is a square root. Right. Now from here you can adjust and simplify that. Okay, we will be able to obtain, hold on, let me see whether I got that correctly. If I let me check for a while in case I make mistake here. Okay, I think I made a mistake on my differentiation. Just let me correct that. Okay, this differentiation is not correct. Okay, let me correct that. It's supposed to be, okay, now that will be a negative 2e. Oh, okay, so that is actually negative 2 et minus e negative t. Sorry, I think I missed out this part here. Over et plus e negative t square. Now that should be correct at this point. Okay, so that will be a plus here. Yeah, correct. So there's a plus here. Let me change that. And then at the top here, I will need to introduce that extra term. So that will be a 4 et minus e negative t square. All right, so that's how it look like. Okay, from here onward, I can move this outside of the square root. So that will be a square, and then that will be a 3 here, I think. Yep, correct. Is that a 3 here? Okay, just let me check for a while. That will be a 3. Yes, correct. That is nothing wrong. My y is correct. Let me check for a while. Yep, correct. So this part here, I will get a square and then a 3 here. So therefore, my answer will look something like this after simplifying. Okay, so let me simplify this. Right. Okay, hold on for a while. Okay, so by simplifying this, I should be able to get like the 4 I can also factorize out. So therefore, this part I will get a 4 pi. Okay, I'll get a 4 pi here. And then in this case, I will be able to get et minus e negative t over et plus e negative t to the power of 3 here. Okay, and then what is found inside after factorizing, I will be able to get e2t. All right, so minus 2, yes, correct, minus a 2, and then minus a 2 plus a 4, that is plus a 2. So minus 2 plus a 2. And then finally, I will have my e negative 2t here, square root. All right, so I hope that's clear. With respect to dt, yep, I almost missed out my dt there. Okay, and then lastly, you will notice that these sections can be factorized. So this whole thing can be factorized. Let me write down the side here. e2t plus 2 plus e negative 2t can be written as et plus e negative t square. Right. So that is a square. And then if you square root that, you will only get et. Okay, you only get et. Yeah? So from here, you will get 4 pi integrate from 0 to 1. And then finally, we will get, all right, so this is a bit crowded here. So please forgive me on that. This part will be negative t over et. Okay, maybe, right, hold on. The location is just too small to write here. Just let me clean it up. I think I'd rather write somewhere that you can see it clearly. Okay, so therefore at this point we don't really need this result anymore. Okay, we don't really need this result also, so let me clean it up. And then finally I can conclude all this result here from here into here. So therefore the final answer will be 4 pi, integrate that from 0 to 1, and then we will get et minus e negative t over et plus e negative t to the power of 2, because we cancel off 1 from here, and then with respect to t there. And then there you have it. We managed to prove that the surface area when c is rotated through 2 pi about the x-axis, right? Okay, so I hope that is clear. Now next, I'm going to solve this integration using the instructions given. So by using substitutions, or otherwise, of course, we are going to find the surface area in terms of pi and e. Okay. Now, once we have obtained this, okay, let's look at how to get that. Let me clean this up. All right. So let's look at this, number 2. Okay. Now the surface area, using the substitutions of u equal to et plus e negative t, we're going to start off by differentiating this with respect to t. That will be et minus negative et. Okay, you will see that from here, I can simply say that like et minus e minus t here, dt is the same as du. Therefore, I can replace this section here. You can see et minus negative et dt can be replaced using du. All right. Now, therefore, the surface area given by 4 pi 0 to 1. Okay. Now, before that, I forgot to change my lower boundary and upper boundary. So let me try to change it before I write down the lower boundary and upper boundary. So changing the lower boundary and upper boundary, we will let when t is equal to 0, because this is in term of t. So when t is equal to 0, therefore u is equal to 2. And then when t is equal to 1, okay, so when t is equal to 1, then therefore u will be equal to so e plus 1 over e, e plus 1 over e, right? Okay, so I'm going to put this value in. So t equals 0 is a 2, and then when t is equal to 1, then that is e plus 1 over e. Okay. Now that will be our upper boundary, lower boundary. And then now all we need to do is just substitute this u. So therefore it will be du over u squared. So the whole expression can be converted into du, the numerator is a du, whereby the denominator is a u square. And then integrating this will be pretty much a piece of cheesecake. Okay. Now from here we will get 4 pi. All right. Now that will be a negative 1 over u. E plus 1 over e, 2. Right. So we can substitute the value that we have. We're going to substitute the upper boundary first. Now therefore that would be a negative 1 over e plus 1 over e. 1 over e. And then subtract off with 1 over 2. Okay, and then of course by rearranging this and then touch up a bit on the algebra so that it's more neat in this case. So I can write it down as, okay, now take for instance, I can write it down as 4 pi first, 1 over 2 minus, I could change it to e 1 plus e squared, for instance, in this sense. Or I can finalize this as 2 pi 1 minus 2e over 1 plus e square. Okay, 1 plus e square in this case. Right. Okay, so I hope that's clear in this case. Of course, some of you may like to re-describe this in a different way. So you might want to describe it like this: e minus 2e plus 1 here, plus 1 over 1 plus e square, like this. And then you will notice that the numerator can be factorized further. So therefore, this one you can actually write down as e minus 1 square over 1 plus e square there. All right. Okay, so I hope that is clear. Now that will be your surface area in terms of pi and exponential value, right? Now I hope that's clear. I'm going to move on to the next question shortly. Right, let's take a look at question 6 now. Right. Okay, so here we have a cubic equation, x3 minus x plus 1 has roots of alpha, beta, and gamma. Now, using the relation x equal to y to the power of 1 over 3, we need to show that the equations, the cubic equation, in term of y has roots of alpha cube, beta cube, and gamma cube. Therefore, or hence in this case, we're going to write down the value of the sum of all the uh, cubic roots. Okay, so let's start with the first one. Okay, now since this cubic equation has a roots of this, so usually the normal practice is we are going to write down the sum of all the roots. For instance, alpha plus beta plus gamma based on this cubic equation as a 0. In this case, you can see that very clearly. Don't forget to always list this down with all your terms, even though there are some terms that are missing. So here you have like a 0 with a x square minus x plus a 1. So you can see that the coefficient for x square is 0. So therefore, coefficient of x squared represent the sum of all your roots. And then we have the sum of all your products, which is given by a -1, which is located at the coefficients for x in this case. Right? And then lastly, we also have alpha, beta, the product of all your roots, which is equal to -1. Okay, so I hope that's clear. Right, now next we're going to use this relation. Now using this relation, all we need to do is just substitute this equation. So substitute this equation into this equation here. Alright, let's give it a try. So therefore, that will be y to the power of 1 over 3 to the power of 3. And then therefore this is, this one will be y to the power of 1 over 3 and then plus a 1 equal to a 0 there, right? Now, from here, we notice that this is actually y minus y cube, cube root, sorry, plus a 1 equals 0. And then, of course, if you like to get rid of the cube root, usually we will purposely arrange them on one side, those with roots on one side, and then those with non-root on another side. And then now typically the way we deal with this is by introducing a cube on both sides. Okay, so therefore we will have a y here, and then you will have a 1 plus 3y plus 3y squared, and then finally you have y cubed there. And then if you rearrange that, that would be 3y squared plus a y cube. I missed that out just now. And then I will have 2y plus 1 equal to a 0 there. Now I managed to show that by using this relation, I should be able to obtain this cubic equation, now which is shown here. Right. Now next, I need to prove that this cubic equation has roots of this. Okay, so by using this relation here, now since x has all the roots of alpha, beta, gamma, so therefore the first root for y, okay, the first root for y will be, I will write down as y1, the first root for y, which is y1, 1/3 is equal to, let's assume that the first root for x is alpha, so I will write that as alpha. Therefore, this implies that the first root of y is actually given by alpha cube. Then you can continue on with the second root, y2, is actually equal to beta, for instance. If it is beta, then your second root will be beta cube. And then, of course, you notice that if you have the third root, therefore, gamma, so gamma to the power 3. So from here, we have proven that the roots alpha, therefore, alpha cube, beta cube, gamma cube are the roots for equation number 1 here. Okay, equation 1. If you label it as equation 1, right? And then there you have it. And then lastly, in order to get the sum of all their roots, so the sum of all their roots can be obtained by looking at the coefficients. So therefore, this one here I will write down as the sum of all their cubic roots. So therefore, in this case, the sum of all their cubic roots can be obtained by looking at the coefficients for y squared. That is a negative 3 here. So we always put a negative sign here. Then there you have it. That is the first answer there, right? So I hope that's clear. I'm going to show you number 2 now. Let me get rid of this. Okay, now I'm going to write down whatever I have previously. So this is negative 3. Okay, that's what I have. Now I need to obtain the second part. So s negative 3, where the notation for the summation of all their roots are given as such. So s negative 3 basically mean alpha negative 3 plus beta negative 3 plus gamma negative 3, which is the same as 1 alpha 3 beta and gamma. Okay, and then of course you can do a bit of restructuring here. Therefore we get this. Okay, all right. Now, what does this actually mean? This simply means that the numerator, so I can write down the numerator, beta 3 is the product of all the roots for this. So the product of the roots can be obtained by reading the coefficients for y. That is typically 2. Mhm. And then the product of all their roots. So the products of all their roots can be obtained by looking at the last constant there. So starting from negative, positive, and then the last one is a negative 1. Therefore, we can conclude that the summation for this is actually given by a 2, which is given by this. This is the same as alpha cube, beta cube, the sum of all this divided by here, alpha cube, beta cube, and gamma cube. So therefore divided by negative 1, therefore your answer is negative 2. So I hope that is clear. Right, now next I'm going to show you the third one. Okay, so for third one, we have S6. So S6, first of all, by using this notation, it simply means alpha 6 plus plus beta 6 plus gamma 6. Now what that means is actually alpha 3 square beta 3 square plus gamma 3 squared. Now you can use one of the identity for the sum of square. So the sum of square here, I can write this down as the sum of, oops, let me write it down here. So the sum of square for all this can be written as the sum of this. So the sum of square can be written as the sum of all this square minus of 2 times the sum of all their products. So all their products, right? So from here, this is typically, okay, hold on, just let me rewrite that. So this part here is typically S6. And then from here, this is the sum of all their roots, which we have already found out from here. So the sum of all their roots, I'm going to rewrite that again, that is negative 3. And then the sum of their products, which is actually given by a 2 here. So therefore from here, I'll put square minus of 2, 2, and then that will yield a 5 there, right? So I hope that's clear. Okay. All right. Now the last part is more interesting in a way, right? Okay. So you can check this out. I'm going to erase it, and then I'm going to show you how to obtain S9 here. Okay. So let's obtain S9. So for S9, now S9 typically means alpha 9 plus beta 9 plus gamma 9, of course. Okay. Now that is typically alpha 3 to the power of 3 plus beta 3 to the power of 3 here plus gamma 3 to the power of 3. Okay. Now, how can we make use of these equations to actually obtain this easily? Okay. Now, take for instance, if alpha cube is one of the roots here, so therefore we can put alpha cube as the y. So therefore, this would be something like this. Plus a 1 equal to 0. Now that will be our first equation. Then of course you also have beta cube. Beta cube plus 2 beta cube plus a 1. Now that will be our second equation. And then of course you also have gamma cube. Now that will be our third equation. So from here, if you sum up 1 with 2 with 3, we actually get the sum of all these cubic roots, which is actually the same as S9. So if you sum up this is actually S9. And then you sum this up here, this is actually 3 S6 because it's a sum of alpha 6. And then this part will be a sum of 3. 1, 1, 1, so plus a 3 equal to a 0. And then by rearranging, we found that S9 is actually equal to negative 3 S6 minus 2 S3, sorry. S3, and then finally minus 3. So from here, all we need to do is just substitute our previous result, which is 5 minus 2 S3. Okay, so S3 is basically, this is actually S3, the sum of all your cubic roots. So therefore, that is negative 3 minus a 3. And then that would yield, let me see, what do we have? Negative 15, negative 18, plus a 6, so negative 12 then. All right, so there you have it. So the value for S19 is negative 12. All right, so I hope that is clear at this point. All right, I'm going to move on to the next question shortly. All right, question 7 is the solutions to differential equations. In this case, we are dealing with second order differential equation. This is a inhomogeneous second order linear differential equation, right? Ordinary differential equations to be precise. Okay, right. Now, first of all, when you are given an inhomogeneous second order ordinary differential equations, so firstly, we're going to work out the characteristic equations. So the characteristic equation, we'll start off by looking at its characteristic equation. So the characteristic equations, we're going to consider the homogeneous section here. So it has characteristic equations of this one here, minus 1, equal to a 0. Right. So that will be its characteristics equation. And then we are going to solve this one here. So you have a 5 lambda uh, minus 1. Let me see whether I got it correct. Oops, that is 2. So 2 lambda minus 1 equal to a 0 there. So in this case, it will be a plus 1. All right, so there you have it. From here, we notice that the lambda is given as negative half and 1 over 5. Okay, or you can simply write as negative 0.5, 0.2 here. All right. Now, knowing that, therefore the complementary function, or in short, I'll write it down as CF. Complementary function is given as this is x in terms of t. So I'm going to write down its complementary functions, or h x hash in terms of functions of t, and then that will be given by a e negative 0.5t plus b e 0.2t, where my a and b are all real numbers. Okay, so I hope that's clear. Right. Now next we're going to deal with the particular integral. Right. So for the inhomogeneous sections, because the right hand side expression is a linear equation, so therefore we can make assumptions. The particular integral in this case can be written as y equal to mx plus c, in the y equal to mx plus c form. So I can write it down as mt plus c. Then of course I need to go through the differentiation, and then lastly my second derivative, and then after that I need to substitute all this result here uh, back, let me call this equation number 2 back to equations number 1. Okay, so knowing that, I will have 10. My second derivative is 0 plus 3. My first derivative is m, and then minus x, which is mt plus c. Okay, that should yield t plus 2. All right, so from here we will have a negative mt plus 3m minus c, which is equal to t plus 2. Okay, and then you would notice it quite directly by comparing the coefficients for t. We know that m must be equal to negative 1. And then if m is a negative 1, so therefore the c must be equal to, let me see, what do I have here? Negative 5 then. Therefore, the particular integral is given as negative t negative 5. And then the general solutions. So the general solution, I'm going to write down here. The general solutions for these second order ordinary differential equations will be given as, so the general solution xt is actually the sum of its complementary functions and its particular integral. So if you add them up, we have a e negative 0.5t plus BE 0.2t, and then minus a t minus a 5 there. Right. So I hope that's clear. Okay. Now next, I'm going to obtain the specific or particular solution given the boundary conditions or the initial conditions here. Right. So I'm going to pause here for a while, just for you to check the process. The first part is always to obtain the complementary function. The second part is a particular integral. All right. Okay. Now getting the last part is not that difficult. So I just going to erase this section here so that I can write down the last sections here. Okay. Right. Now, given the initial conditions when t is equal to 0, x is equal to 0. So t is equal to 0, x is equal to 0. So all I need to do is just substitute this one into here. And then therefore I will get a plus b. And then t is 0 minus 5 is actually equal to 0. So therefore I have a plus b is equal to 5. Now that will be my third equation here. Okay, I also noticed that when t is equal to 0, the dx dt is equal to 0. So therefore, I need to obtain my first derivative. So my first derivative here would be negative 0.5 a e negative 0.5 t plus 0.2 b e 0.2 t minus a 1. Now that will be my first derivative. Okay, so I'm going to substitute t equals 0. Therefore, I will get negative 0.5a plus 0.2b minus 1 must be equal to a 0. So therefore, I'm going to simplify this a bit. I think if I multiply by 2, I should be able to um, by 10 then. Okay, I think multiply by 10 will be much more better. So therefore, this is negative 5a, 2b. So by 10, that will be a 10. That will be my fourth equation here. Right. So therefore, by solve 3 and 4, no matter how you solve it, you should obtain a equal to. Okay, let me see. 2 here. So that is a 7. So 2, 10. So therefore, a is equal to. Let me see here. Did I get it right? If I multiply by 10, that is a 2, that is negative 10. Yes, correct. From here onwards, if I solve this, just let me check properly if I got it correct. Okay, if I solve this correctly, then okay, so a is actually equal to 0. Okay, a is equal to 0, and then therefore b is equal to 5. Okay, so from here we can conclude that the particular solution will be given as xt is given as since a is 0, so therefore it's only 5e 0.2t minus a t minus a 5 there. So that will be our particular solutions. All right, so I hope that is clear. All right, I'm going to move on to the next question shortly. All right, question 8 is a mathematical inductions question. Okay, let's get started with this. All right. So proof by mathematical inductions that for all z that is not equal to 1 and all positive integer n, okay, for these expressions to be true, or these equations to be true. Okay. First of all, we can let usually I will start from here. So we'll let Pn represent the proposition. Okay, so represent the propositions that these Okay, so Pn represent the propositions about this equation here. All right, so we get to check out for 1, right? Sorry, n can be 1, yeah, except for z is equal to 1. So let's try P1 then. Right? So P1 basically means on the left hand side. Okay, so the on the left hand side of the expressions, basically it means when n is equal to 1, so therefore P1 is actually referring to the first term, which is a 1. Right. Now let's see whether that is true. On the right hand side of this expression, when n is equal to 1, so that will be z1 minus 1 divided by z minus 1. And then here we can eliminate both of this because z is not equal to, oh yeah, I need to write down this specification. Z is not equal to 1. Therefore, we can simplify that. Yes, that is a 1, which is the same as what's suggested on the left hand side. Therefore, P1 is true. So this implies that P1 is true. So this proposition is true at this point. Okay, so I hope that's clear. Right. Now next, okay, yeah, maybe I'll write down in a different colors so that you can recognize the intermediate conclusions. So P1 is true. All right. Okay. Now next, we are going to assume P okay, assume. So here I will assume that PK, okay, PK is um, is true. Okay, I will assume that PK is true. Should I assume PK is true before that? So I assume that PK actually represent 1 plus Z plus Z2 plus ZK plus 1, and then is equal to ZK minus 1. Okay, ZK minus 1 divided by Z minus 1 here, where the Z is not equal to 1. Okay, so I assume that PK represent this proposition. I will make assumptions that we can assume that this is true, right? So we're going to come back later on to check whether this is true or not based on our assumption, and then we're going to work out the propositions for PK plus 1. So PK plus 1, basically on the left hand side. Okay, so PK plus 1 is basically 1 plus Z plus Z2 plus ZK minus 1, and then the next term, which is ZK in this case. Yeah, ZK. Or you can say that it's actually ZK plus 1 minus 1. Okay, and then on the right hand side, we have ZK minus 1, Z minus 1. Okay, and then you have to add up with the next term, which is ZK. So the next term is ZK. Right. So by doing the algebraic manipulations here, so we will get ZK minus 1 plus ZK plus 1 minus ZK divided by Z minus 1. And then by simplifying this, you will get ZK plus 1 minus 1 divided by Z minus 1, where the Z is not equal to 1 here. Yep. So therefore, you will notice that left hand side and the right hand side is exactly the same. So therefore, this So pk plus, oops, let me change it. Therefore, from here we have an intermediate conclusion here. So pk plus 1 is true. Now, because this is true, it implies that pk is also true, right? And then we know that p1 is true. Therefore, by using principle of mathematical induction, in short, therefore, we can conclude that yes, these propositions, so I'll write down in short. Therefore, we can conclude that the proposition n is true for all n that are positive integer, where z is not equal to 1 there, right? Not equal to 1 there, right? So I hope that's clear, right? Okay, so those line in blue, make sure you write down in the exam there, right? Okay, now that's how we carry out the mathematical induction. Okay, now next I'm going to show you the section 2. All right, let's look at second section here. Okay, all right. So by letting z equal to half cosine theta plus I sine theta here, we have to apply the Moore theorem to deduce that the summations of this series is equal to this trigonometry ratio here. Right? So how are we going to make use of the equation that we have proved using mathematical induction, right? So by letting z equal to this, therefore, we can actually write down 1 plus z square plus until z n minus 1 here. This whole thing can be written as 1 plus z, which is actually half, theta plus I sine theta plus half square. All right, don't forget, because this is to a power 1, this is to a power of 2. Oops, I think I accidentally wrote down something wrong. So there should be a cosine, sorry. That's a cosine plus I sine theta plus 1 over 2 square, and then cosine theta plus I sine theta to the power 2, and until 1 over 2 to the power n minus 1, cosine theta plus I sine theta to the power of n minus 1. Okay, and then don't forget, this summation is the same as zn minus 1 over z minus 1. All right. Okay, now what I want to show you here is that what is the connections between this series here and the one requested in the question itself. So you can see that here we are only interested in the series that involve sign, only involve sign. So the sign are attached to the imaginary section, right? Now before that, where can we apply the deMoivre's theorem here? So we can apply the deMoivre's theorem here. We can actually write it down. The first one we don't really need to do anything here. So you can see that that is typically just cos theta plus I sine theta plus, of course, this is 1 over 2. That will be cos 2 theta plus I sine 2 theta. That's how we apply the Morse theorem. And then we have 1 over 2 n minus 1 cos n minus 1 theta plus I sine n minus 1 theta. Okay, so there you have it. So in this case, basically if you wish to get the sine component, so sine component, we will have something like this. So I'm going to write it down here. You have 1 plus half cosine theta plus 1 over 2 square cosine 2 theta plus until n minus 1 cosine n minus 1 theta. Alright, now those are your real parts. You can see these are the real parts, whereby you have the imaginary part. So the imaginary part will be here. We start off from the half sine. Okay, I think I just take out the half then, since all of them have. Okay, never mind. The half should be put inside there. It's easier to see. So half sine theta plus half a square sine 2 theta and so on and so forth until I have half n minus 1 sine n minus 1 theta. Okay, so those are the this part will be the real, this part will be the imaginary section. And then you can check out the imaginary section here. That typically represent the summations of this series there. Okay, um, n terms. Okay, n term, because it started off from m equal to 1. So when m equal to 1, you have a half sine theta and so on and so forth there, right? Okay, so bear in mind what we need is the imaginary section. So how do we get the imaginary sections then? We can get the imaginary sections from this expression on the right hand side. Okay, so I'm going to pause here for a while. Make sure you are able to show these connections clearly, and then I'm going to rewrite this section here as half m sine m theta, so which is actually the summations of m equal to 1 until in our case is up to like n minus 1, for instance. Okay, until n minus 1, right? Okay, so until n minus 1, right? All right, now that's the first sections there, right? Okay, if you want to write this one here in terms of summations, that is typically half m cos m theta. That would start from 0 then, okay, until n, because there are n terms there. Yeah, there are n terms there. All right, but this one have n minus 1 terms. All right, so I hope that is clear. Now from here, we are only interested in this imaginary section. So I'm going to work out the imaginary sections for this one here. All right. Okay, I'm going to pause here. I'm going to clean up a bit, and then we're going to focus on the right-hand side expression. All right, let's look at the right-hand side expression. So the right-hand side expression is Zn minus 1 over Z minus 1 here. Now, there are many ways to deal with this. Bear in mind, we are still interested to get the imaginary sections out of this expression here. So you can either apply Euler form or the argument form in this case. Okay, take for instance, if I'm using Euler form, for instance. So if I use Euler form, then it would be okay. Should I be using Euler form? Let me see here. Okay, yeah, we can actually use Euler form here. So if I use Euler form, this z here is written as half I theta. So half a I theta. Okay, so it's easier for me in this case. So I'll write down as E I theta as a z n here minus 1 over half a I theta minus 1. Okay, now from here onwards, yeah, that is typically up to you. For me, yeah, usually I would prefer to maybe write down in this form, I theta minus a 1, for instance. And then my denominator, maybe yeah, you can actually write down like this, minus a 2. Okay. If you do it such a way, basically you're saying that you are going to multiply your denominator by 2, and then at the same time your numerator you must multiply by 2 then. So if you are doing that, therefore we will have to change a bit. This will become a 2, and then this part also I need to multiply by 2 there. So therefore, in this case, I would have something like this. This part I will have to change now. Okay, so that will be 1 over 2 n minus 1 there. Okay, 2n minus 1 there, right? Okay, now from here onwards, I need to rationalize. Okay, to rationalize, this is what I'm going to do. I'm going to multiply this whole thing by e negative I theta. Okay, that's how we rationalize usually. Okay, so from here onwards, we will get. Okay, so from here, we will have to do a bit of manipulation here. N minus 1. Okay, so from here, you will get, okay, exponential. Is that I? Yeah, correct. So there's a I. So therefore, there will be a I n minus 1 theta. Okay, and then after that, you have your 2 e negative I theta. And then after that, I will have negative, so I need to multiply this, multiply with a 2, so therefore 1 over 2n minus 2 e to the power I n theta. And then finally I have my 4. Okay, and then the bottom part here, I'll get a 1 here. Of course, I'll get a 1, and then plus a 4, I'll get a 5. And then after that, I'll get myself a 2 e I theta plus e negative I theta there. Okay, now the I theta is very important. So this I theta here basically is um, you can actually get the answer shortly. So you can see that I'm going to write it down here, but I'm going to erase it very quickly here. Okay, maybe I'm going to write, let me see where am I going to write this. Okay, I'm going to write it down here. So E theta plus E I negative I theta is basically cos theta plus I sine theta plus cos theta minus I sine theta. So you can see that this result, this whole result here, can be simplified into this. So it can be simplified into 2 cosine theta. So this whole thing can be simplified into 2 cosine theta. All right, and then therefore, I can rewrite the denominator as 5 minus 2 times 2 cosine theta. All right. Okay, whereby my numerator, okay, let me touch up on my numerator here. Okay, let me get a longer line here because there's too many things to write later on. Okay, so for this one here, I'm only interested to get the imaginary part. So here I'm going to write down specifically imaginary sections for this Cn minus Cn1 here. Just the imaginary section. So the imaginary sections will be 1 over 2 n minus 1. Now we know that this one can be written as cos and I, so therefore that must be a sine n minus 1 theta, and then a minus 2, also the same, sine, this is a minus theta, so therefore this one become a plus theta. Okay, and then next I have my 1 over 2 n minus 2. Also the same here, I'll have sine n theta. And then finally, finally a 4 is a real section, so I don't really need that. So I just need to collect all the imaginary sections. So these are all my imaginary sections, and then I'm going to touch up this. Okay, so I'm going to touch this up so that we can get a nicer answer here. So therefore, the final answer here I can write down as n minus 1 sine n minus 1 theta plus 2 sine theta minus 1 over 2 n minus 2 sine n theta, and then finally divided by divided by 5 minus 4 cos theta there, right? Okay, so that's the one that we have. Now we're going to conclude. We will say that the summations from m equal to 1 until infinity, don't forget, 1 over 2 m sine m theta is basically equal to this. Okay, so it's basically equal to this one here, or whereby the n would typically reach 0. Sorry, reach 0. What am I talking about? It will reach infinity. So when the n reach infinity. So when n reach infinity here, these sections will be 0. These sections will also be 0. You will notice that for limits, okay, I think I put down, how should I write that? Let me write it down properly. The formal way of writing this down would be something like this. I would say limits um, as n approach then. Okay, limits, yeah, correct. Limits m approach infinity for the summations of this m starting from 1 until n, sine m theta. Okay, all right. So as the m approach, as the m approach, not the m approach, sorry, I wrote it down wrongly, as the n approach. So as the n approach infinity, therefore all this n will approach infinity, okay, and then as it approach infinity, therefore all this term will be equal to 0 there. So therefore this will become a 0 plus 2 sine theta. This would also become 0 divided by 5 minus 4 cos theta. And then, of course, you can simplify that as equal to this. Okay. And then there you have it. There's a proof by using deMoivre's theorem here, right? So I hope that's clear. Yeah, I'm going to move on to the next question shortly. Okay, let's look at question 9 now. Okay, it is given that E is an eigenvector of matrix A with corresponding eigenvalue lambda. All right. Now, what that actually mean is AE is equal to lambda E. Now, the E is the eigenvector, and then the lambda is the eigenvalue. Right? So the first one shows that E is an eigenvector of A square with corresponding eigenvalue of lambda square. So in order to get A square, all you need to do is just okay. So in this case, you can multiply both sides with A. All right, and then lambda is a scalar, so therefore you can arrange it in such a way. Right. So this part will become A square. And then we know that AE is equal to lambda E. Therefore, you will get lambda square E. Okay, so therefore, we have verified that therefore the eigenvector of A square, eigenvector of A square is E, and eigenvalue of A square is lambda square. You can see from here. Right? So that's it. That's the first question there. Right? So I hope that's clear. I'm going to move on to the second question now. All right. So let me erase that. Okay. Now, second question. The matrix A and B are given as such. Okay, we are given this. Where I is a 3 by 3 identity matrix and n is a non-zero integer. Okay, so non-zero integer, I'll just write it down here. Non-zero integer. Okay, where n is not equal to 0. Okay, right. So find in term of n a non-singular matrix P and a diagonal matrix D such that it satisfies this diagonalization equation, which is B equal to PD P inverse. Okay. Now, first of all, let's focus on the B here. So B is actually A plus Ni square. Okay. Now that is the same as, you can actually expand that, so which is the same as this. You can write AI or IA, it doesn't matter because the answer is still is the same as A. Okay. So from here you know that I square is basically just I. Therefore this can be simplified as 2NA plus N square. Yep. Okay. Alright. So that is a relationship there. All right. Now, in order to, okay, now let me write down here, this B. So in order to get the eigenvalues, okay, eigenvalues of B, okay, so the first eigenvalue of B will be lambda 1, lambda 1B, okay, is actually equal to the eigenvalue for A square, which is lambda square here. And then this is the eigenvalue lambda, and then the eigenvalue, this one I forgot to write, eigenvalue for identity matrix is 1, so therefore that's just n square. Right, now those are the eigenvalues for B in this case. Okay, maybe I don't need to write 1B, just write B here. Okay. All right. Okay, now that is how it actually look like. Okay, now we have to figure out what are the eigenvalues for A in this case. Yeah, I should write down these are the eigenvalue for A, whereby lambda A is actually equal to lambda there. So therefore this can be written as lambda square plus 2n lambda plus n square here. Okay, so let's figure out the eigenvalue for matrix A here. To get the eigenvalues for matrix A, we will need to solve this equation here. Determinant of I lambda is actually equal to 0 there, right? So from here, all we need to do is just right. So the first one will be lambda 1 3 here, 0 2 n minus lambda 0 0 0 3 n minus lambda equal to 0. Determinant is equal to 0, right? And then that determinant is simply n minus lambda, 2n minus lambda, and 3n minus lambda. So which means the lambda is actually equal to n, 2n, or 3n in this case. Therefore, we're going to substitute this for lambda is equal to n. So our eigenvalue for b will be n squared plus 2n squared plus another n squared will be equal to 4n squared. Oops, it's not 4n squared. It's actually 2n. Yeah, 2n squared. Right, and then you're going to repeat that for 2n. Right, so for 2n, you will have 2n here plus 2n by 2n plus n squared. Right. So this one will be like 3n squared because it's 9n squared here. And then lastly, for lambda equal to 3n, our eigenvalue will be 3n squared plus 2n by 3n plus n squared. Right. So that will be like, what do we have here? It's a 9, 15, 16. So that is typically 4n squared. Right. And then there you have it. Those are the eigenvalues for B. So I'm going to write it down here just as a reference. Eigenvalue for B is 2n squared, 3n squared, and 4n squared. All right. Okay, so we are almost done. All right. Okay. Now the next part is to obtain the eigenvector for A. Right. So the second step is, okay, we're going to pause here for a while for you to verify your own answer. And then next, I'm going to work out the eigenvector for matrix A first. Because the eigenvector for matrix B is exactly the same as eigenvector for A in this case. Alright, so if you're ready, let's erase off this. So the second part, we're going to work out the eigenvector for A. So for eigenvector for n lambda equal to n, so the eigenvector will be equal to this. It would be n minus n, 1, 3, and then you have 0, 2n minus n, 0. I think that is too close already. Let me change it. That's a 3. And then 0, 0, and then finally 3n minus n here. Multiplied by e, which is equal to 0, 0, 0 here. Okay. So from here we can simplify that as n 1 3 0 n. Okay, this is 0, sorry, not n. 0 0 0 2 n. Multiply with x y z, actually the eigenvector 0 0 0 here. Okay. So therefore you can actually solve this one here. We will notice that the 2n z is actually equal to 0, imply that z must be equal to 0. And then next we have ny also equal to 0, imply that y is also 0. Therefore we can let, in this case we can let x equal to t, where t are all arbitrary real numbers. Therefore, the first eigenvector for matrix A is written as T 0, 0. You can either leave it like this, or it can be written as T 1, 0, 0. And then most of the time we just write it down in this form. Hold on. Oops. Okay, this one's supposed to be here. Okay. Let me erase off this. Right. Or you can write it down as 1, 0, 0. Right, now that will be our first eigenvector. So I'm going to write down the first eigenvector here. Okay, so the first eigenvector is 1, 0, 0. All right, so we're going to repeat the same procedure again. Okay, so that will be more or less the same in this case. So all I need to do is just erase off this section here. So that will be for n is equal to 2n. Okay, so that will be 2n. This will be 2n. This will be 2n. And then therefore I will have negative n here. And then this part will be 0. And then finally I will have n, this part. Okay, and then I'm going to solve this simultaneous equation. And then therefore I would end up with, in this case, is nz is equal to 0, imply that z must be equal to 0. Okay. Now negative nx plus y plus 3z is equal to 0. Now we know that z is equal to 0. Therefore, we can actually write down y is actually equal to nx. Now you may let your x equal to t, for instance, where they are just arbitrary real numbers. Therefore, we can conclude that our second eigenvector for matrix A can be written as a t, a nt, and then lastly is a 0 there. Or you can factorize that as 1n0. Or you can write it down separately as 1n 0 there. Right, now that will be our second eigenvector, 1n0. Okay. Now lastly, I'm going to repeat that for n equal to 3. So let me erase off all this first. And then I just need to clean up this section. Okay, the answer will be different. And then the same thing here. Right, now I'm going to deal with 3n. So I need to subtract with 3n, 3n, 3n here. So there is a subtraction here, here. All right. And then that will yield the negative 2n. This part is negative n, and then there is a 0 there. And then the same thing, you're going to solve this. Negative ny is equal to 0. Imply that y must be equal to a 0. Okay, and then after that you have 2nx plus a y plus a 3z must be equal to a 0 there. Now knowing that y is equal to 0, okay, knowing that y is equal to 0, therefore we have, I'm going to write down here, therefore we have 3z is equal to 2n x here, right? So you can actually let, if you want to do it simply, you can let your x equal to, for instance, 3t. That will be much more easier to gauge. So where the t are all real numbers. So since x is equal to 3t, therefore z must be equal to 2nt. And then lastly, our last eigenvector for matrix A can be written as 3t. The y is 0, and then the z is 2nt. and then you can factorize the t, 3, 0, 2n, or we can simply summarize that as this. Okay, now that will be our last eigenvector for matrix A, and then that will be 3, 0, 2n. And then by arranging all this in the matrix form, we will be able to obtain the diagonal, sorry, not the diagonal matrix, the model matrix P. Okay, so I'm going to write that down here as a summary. Once we've done this, we can say that therefore the diagonal matrix can be written as this: 1 n 0 3 0 2 n. Okay, and the diagonal matrix is basically just the eigenvalues for the matrix P, which is 2n square 0 0 0 3n square. You don't have to write in this form. You can just write as 9n squared. All right, and then there you have it. Those are the model matrix and the diagonal matrix. All right, so I hope that's been useful. I'm going to move on to question 10 now. All right, question 10. Okay, now we have two curves, C1 and C2 here. Okay, where A is a constant that is greater than 2. We need to find the equation of asymptotes of C1, which is this. This is C1. Let's label this. All right, so this is C1, and this is C2. Okay, so the equation of asymptote for C1. Now, one of the asymptote we can get is by observing its denominator. Therefore, one of the asymptote is the vertical asymptote is x is equal to -5. Yep, that's the vertical asymptote. And then the other asymptote that we can get would be the horizontal asymptote, right? Now, to do that, the easiest way is to do this. So y is equal to ax over x plus 5. So all you need to do is just divide everything by x, for instance. Right. And then as x approach infinity, whether it is positive or negative infinity, the y would actually approach. Right, now you can see that as x approach infinity, this value will be 0. So therefore a will be approaching a there. Therefore we have two asymptotes here. The first one is the vertical asymptote, which is x equal to -5. And then the second one, we have the horizontal asymptote, which is y equal to 8. Right, now that's the answer for number 1. Right. Now for the second one, okay, second one is longer. Okay, now we need to find the equation of the oblique asymptote for C2. Okay, now we know that it also share the same vertical asymptote here. So for the oblique asymptote, we will need to usually for me, I will perform the long polynomial division. So let's try out the long polynomial division. Hopefully that is not too long. Okay, so divided by x plus 5. Okay, so here I will have to multiply by x. Okay, so multiply by x here. I will get my x squared plus 5x. So from here, I will be able to get my ax plus, okay, maybe I'll try to factorize this together. So there should be a plus 5x then, okay, plus 5a plus 26. And then finally, all I need to do is just put a plus 5 here, okay, yep, multiply by x, and then that's it. So a plus 5 x plus 5a plus 25, and then that will yield 1. Okay, now from here, therefore, we can describe y for C2 as x plus a plus 5 plus 1 over x plus 5. So from here, this section is the oblique. So you can use that straight away, oblique asymptote is y equal to x plus a plus 5. Alright, so I hope that's clear. Now I'm going to move on to the third question shortly, but before that, let me write down all the answer that I have currently. So for this C2 I can write as y equal to this C2. So y is equal to x plus a plus 5 plus 1 over x plus 5. Okay. Now as for C1, I can also describe that in its partial fraction form. For instance, I'm going to do it here. Yeah, I'm going to do it this side here. So therefore, you can actually write as also perform long polynomial division. So I'm going to put down ax plus 5a. Therefore, I'll get a 5a here. And then therefore, this C1 can be written as a minus 5a over x plus 5. Alright. Okay. Now I'm going to use this result to verify that both the curves C1, C2 do not intersect. Okay, let's try this out. Okay, now the first thing is I'm going to assume that, okay, so for number 3, I'm going to assume C1 and C2 does intersect. So they does intersect. Therefore, we can write down x plus a plus 5 plus 1 over x plus 5 here must be the same as a 5a over x plus 5. Okay. And then by a bit of simplifications, we can cancel out the a, and then we will have 5 here, 1 over x plus 5, which is equal to 5a over x plus 5. Now, since x equal to negative 5 is the asymptote, so therefore we know that x cannot be equal to negative 5. Okay. Therefore, we can actually rewrite this again as x plus 5 square plus 1 is or plus 5a is equal to 0. Okay, and then by expanding this, you have x square plus 10x, and then plus 25, 26, so 26 plus 5a equals 0. Right. Now we want to check its determinant at this point, whether the determinant is more than 0 or less than 0. If the determinant is more than 0, yes, they do intersect. Okay. Now we're going to check the determinant, which is 10 square minus 426 plus 5a here, and then that will be 100 minus what do we have here? We have 26, is it? Yep, 26. So that is 104 minus 20a. Okay, so from here you get a negative 4 minus 20a, and then that is actually negative 4, 1 plus 5a. And then we know that a is greater than 2, so therefore this one must be less than 0. Right, because it's less than 0, therefore we can conclude that C1 does not intersect with C2. Right? Okay, so I hope that's clear. This is question 3. Right, now next we're going to find out the stationary points for C2. Right, now previously for this C2 equation, we can rewrite this C2 as y equal to x plus a plus 5 minus 5a over x plus 5. That's what we have obtained for its partial fraction. And then from here, we can use this format to differentiate to obtain the stationary point more easily. So we're going to perform dy dx. That will be 1, and then plus a 5a over x plus 5 square. Okay, and then we have to equate this equal to 0, right? And then therefore we will have what do we have here? We have x plus 5 square is equal to negative 5a. Okay, negative 5a. Let me see, find the coordinates of the stationary points of C2. Okay, C2. Did I get this wrongly? Let me see. That's a minus 5. X minus 1 over 5. Yep, correct. And then therefore that is equal to this. Okay, I might accidentally stumble on complex number. Just let me check the equations whether it's correct. One more time, just run through the long polynomial divisions again. Okay, so that would be like a plus 5x plus 5a plus 26 plus a plus 5. So the a plus 5x, okay, a plus 5x, and then after that I have 5a plus 25, that'll be a 1. So okay, so there's plus 1. That's my bad there. So this part is plus 1 instead of 5a, so it's 1. Okay, so from here, oh yeah, there's a plus 1. Alright, so from here that will be much more easier. So let me correct this. Okay, so now since this is plus 1, therefore this will be minus 1 then. And then from here onward it will be quite direct. Okay, you will see that x plus 5 square is actually equal to 1. Therefore x plus 5 is equal to plus or minus 1. X will be equal to negative 6 or negative 4 there. Alright. And then for x equal to negative 6, then the y itself will be, let me see what do we have here. So if the x is negative 6, we will have, just let me substitute here. So x plus 5 plus 1 over negative 6 plus 5 here. Okay, so that would be a negative 1 plus a, and then this part here will be negative 1. Yeah, negative 1 also. So therefore, this one will be a minus 2. Right? So when it's 4, so let's see what do we have for 4. Okay, so when x is equal to negative 4, so we put in negative 4 plus 5 here. So therefore, we have a 1 plus a, and then this one is a 1. So therefore, there's a plus 2. All right. So from here, we have successfully discovered the stationary points of C2, which is negative 6, a minus 2, and then negative 4, a plus 2. Right. So these are the stationary points. Right. Here we don't really need to determine the natures of this. Right. Okay. And then that's it for this section here. Right. So I hope that's clear. And then the last section. Okay. 5. We need to sketch the C1 and C2 on a single diagram. Okay, let's try this out. So on a single diagram, just let me put this down here. Okay. Alright. So from here we label this as Y, this is X. Okay, let's start from C1 first. So C1 has a vertical asymptote around here. Okay, so vertical asymptote at x equal to negative 5. Okay, right. And then it also have a horizontal asymptote at a equal to 5. Sorry, y equal to a. So maybe I'll just roughly mark it down here. So that is y equal to a. So firstly, I'm going to sketch the C1 first. Right now, I know that C1 passes through the origin. So therefore, the graph must look something like this. Alright, so that is C1, right? And then for C2, it has a vertical asymptote also at x equal to negative 5, but it has an oblique asymptote at x plus a plus 5. So that would be would roughly be something like this. So let me sketch that. Okay, I would say looks something like this. Yep. Okay, whereby this part here would be this part is when x is equal to 0. So therefore, this is a plus 5 plus 1 over 5. And then when y is equal to 0, this is the value here, right? So what we are interested to plot now is C2. Okay. For C2, okay, for C2, let me check. Now C2, okay, when x is, oops, I think I made a mistake here. Let me check that. This one's supposed to be, when x equals 0, is supposed to be a plus 5. Yep, correct. And then when y is equal to 0, this is negative a plus 5 here. Yep. Okay, now we are good, right? And then we also know that it passes through the y-axis somewhere here. So therefore, the graph for this will look something like this. And then we do notice that there is stationary points at negative 4 somewhere here. Yeah. And then there's also another stationary point somewhere here. I would say it should look something like this. Right. Okay. Right. So I hope that is clear for this question. Now I'm going to show you the last question shortly. All right, our last question, question 11. All right. Okay, let's look at this. This is a polar curve. So C1 has a polar equation, so r squared equal to 2 theta. Given the domain lying between 0 and 90 degree here. Now the point on C1 furthest from the line theta equal to pi over 2 is denoted by P. Now show that at P it satisfies this equation and verify that this equation has a root between 0 0.6 and 0 0.7. Okay, let's give it a try here. Now furthest from the line theta equal to pi over 2 is basically furthest from the vertical line. Okay. Right. Okay. Now to do that, first of all, we have to uh, discover our x component for this polar coordinate. So first one, the x component is actually given by r cos theta, whereby our r is given by square root of this, because theta is positive in this case. So therefore, we should expect the r to be positive most of the time. Okay. Right. So we get to substitute this inside here. Okay. Now for the point to be furthest from the line theta equal to pi over 2, we need to differentiate this with respect to theta. Okay, so that would actually give us, let me see, we will have 1 over 2 theta cosine theta, and then minus of 2 theta sine theta. Right, and then we have to equate this equal to 0 to get the point furthest from this line here. Right? And then by solving this, we will get cos minus 2 theta sine theta here. Okay, and then by dividing cos here, we will get 2 theta tangent is equal to 1. Alright, therefore we managed to verify that the point P will satisfy this equation here. Right. And then we need to verify that this equation has a root between 0 0.6 and 0 0.7. To do that, we will have to arrange this in this manner, and then we will label this as let f theta as a function minus 1. Okay, so we're going to test out for sign change. So f06 here, which is 2 times 0 0.6 tangent 0 0.6 minus 1 here. Okay, so let's give it a try. I think I have, oh, I don't have my GeoGebra here. So let me get my calculator here. Right, now bear in mind the 0 0.6 is in radian mode. Okay, so it's in radian mode. Now because it's radian mode, so therefore it's 1.2 multiplied by tangent 0 0.6 radian by a pi here. Okay, so you will notice that the answer in this case is, let me write it down. So the answer here is actually negative 1.22. Yep, so it's negative 1.22, which is less than 0. And then you can try f 0.7, which is 2 times 0.7 tangent 0.7 minus 1 here. Okay, let's give it a try using the software one more time. So here, if I change it to 1.4, and then this is 0.7, then okay, that is still a negative. Okay, hold on. has a root between 0.6 and 0.7. Did I get that right? Tangent 0.7. The 0.7 is a radian mod. Okay, hold on, just let me check that. Alright, after checking with my calculator, I found that there's an error with my calculator. So after I compute this, the answer for functions with the value of theta equal to 0.6 is, let me see whether I still got that, is a negative 0.179 approximately, which is less than 0. And then whereby for the value of 0.7, the answer is 0.179, which is greater than 0. Okay. So therefore, in this case, we found that there is a sign change. So sign change basically means now in terms of the graph itself. So the graph would sort of cut through the x-axis between 0.6 and 0.7. So you can see that anything 0.6 is a negative, anything above 0.7 is positive. So therefore there's a sign change. And then because there's a sign change, therefore we can conclude that yes, there is a roots between 0.6 and 0.7, right? Okay, so I hope that's clear. We can look at the second sections now, right? All right, it's the second section. I'll find the exact value of theta at Q. So here you have another polar curve C2, which is given by this. Both of them intersect at the pole, which is the origin basically, and then at another point Q there. So we need to determine the exact value for theta at position Q, right? Now for that to be able to be processed or analyzed, we need to equate both of these r squares together. So you can see that this is equal to this. This is for C1, and then for C2 we have r square equal to theta secant square theta here. So therefore we're going to equate this both of this. Okay, so from here I can write it down as is that correct? Yeah, correct. So secant square theta equal to 0. And then from here we found that theta must be equal to 0, which actually passes through the origin or the pole in this case, or secant square theta is equal to 2. That basically means cosine square theta is actually equal to 1 over 2. Now, therefore, from here, cosine theta is equal to 1 over square root of 2 here. But because we are restricted to this domain, therefore all the value for cos is positive. And then from here, we notice that if you use your calculator, it should yield pi over 4. Right? So that will be the exact value of theta at Q here. Right? So I hope that is clear. We're going to move on to the next question shortly. Okay, that's right. So the C2 has these equations: r square equal to theta secant square theta here. So therefore, this one will be theta secant square theta d theta here. Right, so from here I'm going to rewrite this area over this side, and then I'm going to perform the integration by parts over here, so it'll be easier to observe. So area A is given by half. Okay, so half. You can actually take out the theta, which is 2 minus secant square d theta 0 to pi over 4. Okay, all right, so I'm going to erase off this. Okay, so from here onwards, we are going to perform the integration by parts. So therefore, it's quite long here, so I'm going to write down from here. This area will be equal to half. We will have theta, and then there will be a 2 theta minus tangent theta. Okay, subtract off with the same one here, so there will be 2 theta minus of tangent theta d theta from 0 to pi over 4. Okay, and then right, this is what we have. Okay, so from here we can substitute 0 there, okay, which is a 0. And then if you substitute the pi over 4, so we have pi over 4 here. This one will be pi over 2 minus 1. Okay, and then we're going to integrate this one more time, which will be theta square, and integrating this would give us a ln cos theta. Okay, so this is what we have, right? And then after that, if we try to simplify the whole thing, we will get pi over 8 pi over 2 minus 1, and then we have half over here. 0 is a 0, so pi over 4, so pi square over 16. This one here will be ln 1 over 2, so which is actually negative. So negative 1 over 2 here, ln 2, yeah, negative 1 2, right? So from here, we can simplify that as pi square over 16 minus pi over 8 minus pi square over 32 plus a quarter of ln 2, right? And then you can further simplify that as this one will be a 2, therefore it's pi square over 32 minus of pi over 8 plus a quarter of ln 2. Alright, so that would be the area enclosed by both of the curve given in blue color there, right? Okay, so that's all for this P1 paper. I hope you enjoyed the lesson. Alright, if you like what you are looking at, do subscribe and then press on the notifications button to receive the latest video. Alright, thank you very much for watching. I'll see you guys again.